Okay, so today we are continuing from where we left off the last time. We started with Unit 5 or Section 5, which is nuclear physics. Oops. We talked about the atomic model and the experiment carried out to theorize the current model of the atom we have. Then we talked about electrons moving between their orbits and then emitting electromagnetic radiation when they lose energy. Ions, which are formed by either the loss or gain of electrons. Today, we will talk about what's inside an atom, particularly inside the nucleus. So that's 5.1.2, nucleus of an atom. And what we know based on experiments, right, conducted by Rutherford and Niels Bohr, is that they are particles inside. And in fact, this was known earlier as well, but the model, right? So we know that there are particles, there are protons and electrons, but how they are arranged came about by as a result of the experiments they conducted. And so they're particles inside what they called the nucleus, which is at the center of the atom. What? Not nucleus. Right? Which are positively charged. So you've got protons. We're familiar with these guys from chemistry, which are positively charged. And neutrons, right, which don't have any charge. And together they make up the mass of an atom. Right, so both of these guys have mass that is considerable, right? And then you have electrons arranged in orbits around the nucleus. And these guys are negatively charged. In an atom on its own of any element, right, which hasn't undergone any reaction or hasn't been, mingled with, is electrically neutral overall, right? Which means that the positive charges are equal to the negative charges, which means that the number of protons are equal to the number of not neutrons, but electrons, right? And the number of neutrons varies between elements. Right, so as we know, for example, hydrogen, right, has one proton and 0 neutrons and 1 electron. And that is why when you get a hydrogen ion, when it loses its electron, it becomes a positive ion. It is only a proton. All right, so this guy is called a hydrogen ion. or also called a proton. I'm sure there are no questions.
No.
Okay, now one thing is that these subatomic particles, the protons, neutrons, and electrons, well, the protons and neutrons particularly, these guys, because they're present inside the nucleus, they are collectively called nucleons. So there's a term, new term for you, right? Now, there are two sort of values that are associated with atoms. One is the atomic or the proton number. And that is denoted by a Z. Right? And as the name suggests, it is the number of protons in the nucleus of the atom. Right? And then you have the mass or nucleon number, which is represented by an A. For some reason, I don't know. A for atomic would have been better, but that's it. Hmm? And this is the number of protons plus number of neutrons. So since I just told you that they call nucleons, so nucleon numbers, so the total number of neutrons and total number of protons, which gives you the mass of the atom. And therefore, if you want to find out just the number of neutrons, then you would do the right mass number. I wrote this wrong. The mass number minus the atomic number will give you the number of neutrons. Also, any element is represented this way. And X, which is the atomic, which is the elemental symbol, and then you have the mass number going up top here, and the proton number coming over here. Okay.
Yes.
Also, they mention that the electrons of an atom determine the chemical properties of the atom, which we know. And also from chemistry, it is the number of protons that determine which element it is. Right? So you can obviously have a different number of electrons. We get ions out of that. You can have a different number of neutrons, which we'll just talk about, and that will give us isotopes. But you cannot have a different number of protons for the same element. right? If the proton number changes, that means you're getting a different element. Just on a note, in chemistry, when we learned about the relative mass of a proton, electron, and neutron, it was given as the atomic mass unit, and protons or neutrons were given as 1, and electrons were given as 1 over 1839, right? So the atomic mass unit of a proton was 1, neutron was 1, and electron was 1 over 1839. Over here, what they've done is they've given a proton as 1839 and neutron as 1839, and not atomic mass unit but relative mass, right? So relative mass, which basically means that they weigh much more than the electron, and electron is 1. In principle, it's the same thing, but it's a very different way of mentioning it. Okay. Now, isotopes are atoms. Remember what isotopes are, guys?
Yeah.
Tobia, would you care to share?
They are variants of
Variants.
no. They're like the chemical element with like the same number of protons
Uh,
but different number of neutrons.
there you go. Now, chemical element is sort of, weird to say because elements are by definition chemicals.
Ah, okay.
But yes, they are the atoms of elements. You could say variations. You could say variants. I mean, linguistically, that have.
Which is why they have distinct mass numbers.
Well, yes, because they've got a different number of neutrons, right? So their mass is
Yeah.
different. So atoms of elements with different number of neutrons, right? And so their mass is different. And that affects, right, some physical properties. Change or affected, right? Chemical properties, because they said it's on the number of electrons, the chemical properties and the reactions they undergo do not change, right? And in many cases, when we talk about elements, right, isotopes are naturally occurring. Right, like in the case of chlorine, you've got Cl35 and then you've got Cl37, right? And they're present in a ratio of 3:1. And so right, the chlorine 35 being the mass, is obviously more abundant. It's present in more quantity as compared to chlorine 37. It's there as well, right? And so what they do is they take an average mass, and that's taken as 35.5. So that's one example. There are other, and many elements have isotopes, right? By the way,
Yeah.
fun fact: it's given in the book that the word isotopes comes from Greek, and isos means same, and topos means place.
So
So
same place.
yes,
Oh, okay.
okay. Hydrogen has 3 isotopes. So you've got the regular hydrogen with 1 proton and no neutron, so that's there. Then you've got deuterium with 1 proton and 1 neutron. And then you've got tritium. Is that how? Yeah, tritium with 1 proton and 2 neutrons. Right? Now, the H1 is like 99.9% abundance. So that's basically what you get. So these two guys are very rare, and so they are sort of made when required, right?
Sort of what?
They are made, so they are artificially made as well,
Oh, okay.
right? They are naturally occurring, but they're so like, less in abundance that normally, right, you wouldn't notice. Deuterium is called heavy water. And as I said, some physical properties are affected. So its density is more, as you would expect. So it's it's not 1 gram per centimeter cube like regular water, it's 1.108 gram per centimeter cube density. And what's more interesting is that it has a melting point, or freezing as they mention over here, right? So the melting point is 3.8 degrees centigrade, and it boils at 101.4. Now, because what's changing over here is a neutron, isotopes are also called nuclides, right? Some of these guys are radioactive, which we'll talk about later. And so in that case, they are called either radioisotopes or radionuclides. Okay?
Yes.
All right. So there's some stuff here, interestingly, in the IGCSE, slightly, that is given in some more detail as compared to the O level, which is actually good, right?
Yeah.
So next we're going to talk about nuclear energy. And we are going to come across Einstein's famous equation, right? The mass energy equation, E equals to mc squared, right? Where E is for energy, m is mass, and c is the speed of light. Okay, and so what he's saying is that, right, basically energy and mass are interchangeable, and that is how, like, it is also conserved, right? So if there's for a body, right, a change in energy means a change in mass. We're talking about change, we're not talking about increase or decrease over here, right?
Oh, yeah.
So if a body changes, if the energy of a body changes by an amount E, right, so by amount E, the mass will change by amount m, and c is the speed of light, 3 into 10 to the power 8 meter per second, right? 3.0 into to 10 to the power 8 meter per second. And so what this means is it comes to the theory of mass effect. That is an implication. Mass defect. What this means is if mass is lost, it is converted to energy, right?
Yeah.
But the changes in energy and mass in physical and chemical changes are very, very small. So we don't really talk about those, right? Uh, these come this comes mostly into play when we're talking about uh, you know nuclear reactions and radioactive decay, right?
Yeah.
So that is where you really see this happen. We're just going to talk about that. And so what was some you know again an implication of this and understanding from this is that mass or matter in general is a very concentrated store of energy. Okay, with that understanding we come to nuclear fission or just fission. So I'm putting nuclear in brackets, right? And what fission means is breaking or splitting. And so what you understand from this is we're going to talk about the breaking or the splitting of the nucleus, right?
Yeah.
So for this, I'll take you to the text. You're following so far? I don't
Yeah.
I don't believe there's anything other challenging. Haram, you following? The mass energy equation is not given in the O level text at all, I believe. Right? This equation and these numbers are not given in O level either. The rest of the explanation is so we see over here for fission, the heavy metal uranium is a mixture of isotopes of which uranium 235, so you can see that the mass is 235, is the most important, right? It's radioactive. Some atoms of this isotope decay quite normally. What is decay? We'll talk about later, right? It sort of uh, releases energy and splits and forms other elements that are more stable and are not radioactive. Okay, that's what decay is. It happens over time. So when they do that, they emit high speed neutrons. If one of these hits the nucleus of a neighboring uranium 235 atom, and that can happen because neutrons don't have a charge, so they're not repelled by the nucleus. So when a high speed neutron that is emitted by a decaying uranium 235 atom, hits another uranium 235 atom, the nucleus of that second atom may break, right, which is the fission of the nucleus, into two nearly equal, radioactive nuclei. They say that, but when you look at the equation, you're like, that doesn't seem very equal. Often they form barium and krypton. So uranium 235 splits and forms two different elements. It forms two new nuclei, right? And those are barium and krypton. And these both of these, right, into two nearly radioactive nuclei. So these guys, right, aren't. These guys are radioactive as well, and that releases two or three more neutrons. Okay, so you've got uranium 235. It's been hit by, so this neutron is the one that's coming in from the original atom, right? So it's hit with a neutron, and so you have barium and krypton, right? And it's releasing two further neutrons, right? The mass defect. Now they talk about mass defect. They're not talking about mass defect in the O level because they didn't talk about this equation, right? So this is for IGCSE, and that too for the extended syllabus. So the mass defect is large and appears mostly as kinetic energy of fission fragments. They do talk about that. So they don't use the term mass defect. So the fission fragments, right? These guys and the neutrons, they have a lot of kinetic energy. These fly apart at great speed, colliding with surrounding atoms and raising their average kinetic energy. And so the average kinetic energy of atoms or molecules is heat. Or sorry, not temperature, not heat, temperature, right? And so the temperature rises. Note that the total values of the mass and the protons must balance on both sides of the equation. So you've got 92 protons over here, right? And you've got 50 and 30, so that's 80, and 6 and 6, so that's 92. So you've got the same number of protons. And must be balanced on both sides of the equation because nucleons and charge are conserved. So on the left, you've got the total number of nucleons, which is 235 plus 1, which is 236, and the total number of protons is 92. On the right side, the total number of protons is 92, and the total number of nucleons is 144 plus 90, and two neutrons emitted. So you're adding those as well, and that comes to 236 as well. So you're ending up with the same number of protons and the same number of nucleons, or neutrons in this case, right? The total values of A and Z on each side of the equation are equal. So that's something. What happens is if the fission neutrons split other uranium 235 nuclei, so these guys over here, they go ahead and they split other uranium 235 nuclei, a chain reaction is set up. What does that mean? Those neutrons break other uranium atoms, those release neutrons, they break other uranium atoms, and so, right, it's only expanding, as you can see. So one neutron coming in over here, this breaks into fission fragments, so that's the barium and the krypton. The green guy is the neutron, so it's releasing two neutrons, each neutron, right, hitting two other atoms, those making fission fragments, and then, right, releasing two neutrons each. And you can see that will, right, these will affect four atoms, and then four will release eight, and so 8 and 16 and so forth, right? So it will just keep, the reaction will keep, expanding, so to speak. In practice, what really happens in nuclear fission, some fission neutrons are lost by escaping from the surface of the uranium before the chain reaction is set up. The ratio of those causing fission to those escaping increases as the mass of uranium 235 increases. This must exceed a certain critical value to sustain the chain reaction, right? So the number of neutrons causing the fission must be of a certain critical value so that the chain reaction is sustained. Otherwise, something will happen and then it will stop.
What do you mean by critical number?
You mean you need to have a certain number of
Uh,
neutrons that are hitting the uranium 235 atoms and then causing more neutrons to be released, you need to have a certain number of that happening for the chain reaction to occur, which means it's just expanding one after the other. If there isn't enough, right, a neutron might hit a uranium atom here and there, but it's not going to cause a chain reaction.
Okay.
Okay.
Yeah.
Okay, then they talk about the nuclear reactor and then they talk about nuclear fusion. Okay, so what happens in a nuclear reactor? Now, this is stuff that you just need to know, right? So, in a nuclear power station, heat from a nuclear reactor produces the steam for turbines. Uh, right, this is a simplified diagram of a reactor. Oops. The chain reaction occurs at a steady rate, which is controlled by inserting or withdrawing neutron absorbing control rods of boron among the uranium rods. Right? There's also something called the graphite core. Right? It is called the moderator and slows down the fission neutrons. Right? Why do they do that? Because when the neutrons are slower as compared to faster, right, fission occurs more readily. Now, when we talk about slow and fast, we're talking about relative speed, right? We're not putting a number to it. Carbon dioxide gas is pumped through the core as a coolant. In the heat exchanger, the heated gas, the carbon dioxide heats up, it takes up the heat, right, keeping the system cool. And the heated gas transfers energy to pipes containing cold water so that the water boils and produces steam. And then that goes and, turns the turbines. The concrete shield gives workers protection from gamma emissions. We'll talk about that later. And escaping neutrons. The radioactive fission fragments must be removed periodically, so the barium and krypton, if nuclear fuel is to be used efficiently. And then they mention something: in an atomic bomb, an increasingly uncontrolled chain reaction occurs when two pieces of uranium 235 come together and exceed the critical mass. Okay.
Yeah.
So what's happening over here? You have the concrete shield that's protecting from emissions and neutrons, right? The boron rods to control the fission reaction, the uranium rods, which are the radioactive material, the graphite core. What was that guy doing? It's the moderator and slowing down the neutrons. And so you're pumping in cold gas from underneath. That's carbon dioxide gas. It's taking up the heat and cooling, keeping the system cool. Again, cool being a relative word, right? The hot carbon dioxide going in, it's heating up the cold water coming in, and what you're getting out is steam, and that's going to the turbine and then producing electricity. Finally, we've got nuclear fusion. Okay, if light nuclei, light meaning having less mass and rather less mass, as you can see over here, join together to make heavier nuclei, this can also lead to a loss of mass and as a result, the release of energy. So going back to Einstein's equation, the mass defect. Such a reaction has been achieved in the hydrogen bomb. At present, research is being done on the controlled fusion of isotopes of hydrogen, deuterium and tritium to give helium, right? So you've got deuterium over here, right, with a proton and a neutron, tritium with a proton and two neutrons, and combining those two to give you helium, which is inert, it's a noble gas, and the release of a neutron. So fusion can only occur if the reacting nuclei have enough energy to overcome their mutual electrostatic repulsion. Because the nucleus has positive charges, so it's not going to come together easily, right? So only if they have enough energy to do that. And so what they do is when they, like in this scenario, right? It's done at very high temperature, so like over 100 million degrees centigrade, which is not something you're going to get on Earth. So that they collide at very high speeds, enough speed, they have enough kinetic energy to overcome the electrostatic repulsion, not repulsion, sorry. If fusion occurs, the energy released is enough to keep the reaction going. Since heat is required in this case, this is called thermonuclear fusion. Thermo meaning, you know, temperature, heat, and
Yeah.
nuclear is the nucleus, and fusion means bringing together, right? So fusing nuclei of atoms using heat. And then we talk about the sun, right? So the source of the sun's energy is nuclear fusion, right? What's happening in the sun is hydrogen is being brought together to make helium, right? And the temperature of the sun is high enough for that to happen in a sequence of thermonuclear fusion reactions known as the hydrogen burning sequence, right? So this is all stuff. Any questions? Is that clear?
Yes.
Right, so this is all stuff for you to just know. I mean, there is concept over here, obviously, right? Hope that concept is clear. But then again, it's tough to know. So that is the end of 5.1. Then we're going to talk about radioactivity. So I'm giving you guys like a, let's say, 5 minute break. Yeah.
Yeah. Yeah.
So I'll see you guys in 5 minutes, and then we'll continue with radioactivity.
Okay.
All right.
Allah Hafiz.
Allah Hafiz.
So, how long will this class be? Like the next session?
Sorry, could you repeat that?
For how long will the next session be?
At least half an hour, maybe slightly more.
Okay.
Okay.
Allah
Hello?
Hafiz.
Allah Hafiz.